equipment manufacturer, you may want to think about using TM65 to provide that embodied carbon information so you can start think about embodied carbon. Is there a TM65 for Thailand? Not yet. You know what's the beauty here? You can be the superhero to do that. If you want to, you can work with us. We can generate a TM65 for Thailand together. So the manufacturer can start telling you how much embodied carbon a chiller has, a AHU has, essentially free, using an Excel spreadsheet. Okay? So let's think about that. Because otherwise, $35,000 US for every product is super expensive for anybody to think about that. So that's TM65. We also have decarbonization for office building, grid interactive building, whole life carbon guide for building system. Grid interactive building. By the way, you know, one of the discussion in US is abandon natural gas. We want all electric future. Is it happening in here yet, the discussion about all electric future? Huh? On the electric vehicle maybe. But how about the entire built environment, all electric? No more gas? No? Well, in Chicago, where I live, right, we have a decarbonization meeting, so I walk into the decarbonization, sit down, and then next to me are the gas company people, natural gas company people. You know what happened to them? Well, by the way, are there any natural gas company people here? Huh? Monopoly. So none of those people here. Okay, but even if they're here, like, it's not. I mean, I'm just telling you what happened to my city, right? The guy sat next to me, and then the city officials come in, saw the gas people, and said, "Oh, Mr. Gas people, you know, today you can sit there. We won't kick you out of the room, but you are not allowed to talk." Hey, how do you like that? The city of Chicago tell you, you can sit in a meeting to listen only. You cannot talk. But where's the electricity come from? So we did a projection in US by National Renewable Energy Lab. If the entire US go all electric, how much the electric grid have to get larger by? Do you know? About 70%. Whoa, seriously? 70%, how are you going to get there? Wait, what year we want to be net zero? 2050. 27 years from now. Have you do any of those compounding thing? If your growth is 1% per year, 27 years is a lot of growth. In fact, you do the law of 68. 68 divided, let's say if you grow 10% a year, the law of 68 is 68 divided by 10, that means 6.8 years, you double your investment. So if you invest in the Thai stock market and grow 10% a year, that means in 6.8 years, you double your investment. So we want to grow 7%, 68 divided by, say, let's say we grow, 27 years, right? So let's say 2% per year, 34, right? So it's only 2 to 3% a year if you have 27%. The point is 70% size of the electric grid. Say, whoa, wow, that's huge. We're going to increase it 70%. But the growth rate is only 2 to 3% a year in the electricity. It's totally manageable. That's why in US, when you talk to the electric company, you know, number one, they are very happy you go all electric, right? Because the gas company is out. Number two, they totally think it's doable because it's only 2-3% a year. It's not an issue. They can do it. So all electric future. Now I don't know what Thailand's going to do, because if it's not an all electric future, later on you will see you're going to have an issue. Because natural gas will always have that emission, but electricity, maybe right now it emits more than natural gas, but it would gradually drop if it's all renewable to zero. So that would be a problem in the future. As rate 90.1, the energy standard has been ratcheting down, and it will be net zero by 2031. Free version from now. By the way, this is referenced as a coal. Right? So there's an option of the coal to go to zero by 2031. And guess what happened when we talked to the US government and said, look, we are being the superheroes here. We will have an option of go to net zero by 2031. What did the US government say? Thank you very much, but we want it today. So when the government said that to you, what did you say? Oh, I'm sorry, I cannot do it. No! Of course we said, you want it today? Of course we can do it. How stupid we are thinking about 2031. We want to do it today. So by next year, we're going to develop a version of net zero operational carbon building or energy building by next year. But that's not the end of it. We actually now developing an international building code whole life carbon approach standard can be applied to the whole world. A whole life carbon standard that can help all the cities and towns to go to whole life carbon zero. Because the White House want to do it. The current, for those who, I don't know whether you're familiar with US politics, the prior president has no interest. He is not interested in doing anything with natural gas, not interested in anything. This current president is like, let's go, come on. We're going to give you $3 billion to look at embodied carbon. Well, guess what happened when you give $3 billion to the US companies to look at embodied carbon? What do they say? Of course, we are very interested, right? So everybody is interested. White House is starting a buy clean program, buying product that has low embodied carbon. That's just US government. What's the world committing to? The world, most of the world in blue color, committed to net zero by 2050. Just about the whole world, 2050. Now China is 2060, some are earlier. One thing about China, if you don't know, one thing about China is once they set something, they will do it. You know why? Chinese people, if one thing they do not like internationally, they don't like to lose face. They said they want to do it, they're going to do it. And if they do it, you know what's going to happen to US? US going to do it before them. Because the US people never like China to get ahead of them. So this is going to happen. This is what happened to Thailand. At COP26, carbon neutrality by 2050 and net zero greenhouse gas emission by 2065. That is what your country has committed to. Who's going to do it? Do they even know what they're committing to? The technical issue. That's why you guys are the super beings. Why you're the super beings? Because to fill that technical gaps, you need science, architects, and engineers who understand this stuff to execute it. You are not a politician. Maybe some of you are, or maybe some of you are really good politicians in your company too. But you will need architects and engineers to execute the details. How do you do it? How do you get a country, mainly its buildings and infrastructure in our arena, to get to zero? What percentage is most likely the carbon emission from the buildings and the built environment in the area we are in cities? Do you know? Most of the cities, 70% of the emission are from the buildings and infrastructure, 70%. So much of it is under us. That's why we have to be the super beings. I wasn't quite joking. I was a little bit joking, but not a whole lot. When I talk about this morning, we should be the superhumans gonna save the earth. And also the Thai government committed emission 30 to 40% in 2050 from the previous target of 20-25%. You think they are advanced? Look what happened to this country. This is Denmark. Denmark, starting this year, you're going to have to do this. The first circle here is your embodied carbon divided by 50 years. All right? Oh, actually, maybe I should go back. See if I can go back here. Before I go to the next slide, let me tell you what they committed to. The country's commitment is anything starting from January 2023, okay, it's gone already, 3 months ago. Any new construction under 1,000 square meter, you're going to have to achieve 12 kilograms CO2 equivalent per square meter per year for buildings with 10,000 square meters. This is a country code. You cannot, you have to follow. And if you're wondering what is that number, where it came from, it's your embodied carbon for 50 years. Now, a couple of things here you got to immediately pick up. Number one is they are assuming a building life cycle is 50 years. Okay? Now you got to figure this is Denmark. Put your mind when you look at Denmark. Did you see any 200-meter tall tower in Denmark? No. Low rise, right? So 50 years building. So your embodied carbon divided by 50 years is your embodied carbon per square meter per year of emission. And then your operation for the entire 50 years divided by 50 years is your operational carbon. Together, that's why it's in kilograms CO2 equivalent per square meter per year, and it cannot be exceeding 12 because they study a whole bunch of Denmark building and figure out that's probably the ceiling. You're not going to exceed that. There are countries out there already has building codes that limit the whole life carbon of your building, not just operational. I think Thailand just passed the operational energy part of it, right? So they already have operational energy and embodied carbon with a number. You know why do they have that number? Because they want to get to a zero future. They're going to do this 12, 11, 10, 9, 8, 7, 6, 5, 0, 0. That's what they're thinking. That's why there's a number ceiling, because it's going to ratchet it down to 0. That's their Denmark way of thinking. Will that happen to Thailand? If it didn't happen, if it's not yet happened, right? We know it's not what yet, not what. By the way, in U.S., there's only one state, California, has this rule that you have to report their whole life carbon. Most of U.S. is not there yet. But if you don't have that, how are you going to go down to to 0 in 2050? So you have top-down measures force you, bottom-up, like people like us start talk about it, and we do it. But then you have top-down government pressure to make you do it, right? So that's Denmark. Now, what we did, we just kind of looked at the world, what's going to happen from now till 2050. And as a matter of fact, by 2050, you are just a little bit late. You already exceed the 1.5 degrees C. 2040 is already 1.5 degrees C. So if you work with Google, oh, I want to tell you a story. I work with Google, right? Google moved into a building. I said, you know, I'm the consulting engineer for him. It's like, you know, how do you want us to coordinate with the base building? Google said, we want GWP of 150 on the chiller. Look at the base building chiller. What refrigerant do I find out? What do you think? Common chiller today, refrigerant, what is it? 134A, yeah. What's the GOP of that? What's the GWP of that? Greenhouse? Yeah, more than 150. Anybody know the 134A greenhouse gas emission? Or the GWP? Global warming potential? Oh, no Google cheating. It's like 1,300 or 1,400. So that's not 150, right? So I went back to Google and said, hey, they have base building, they have conventional 134A, nothing wrong, you know. But you want 150, right? They said, yes. Luke, you go tell them we want them to change the chiller. What do you think? What would you do if the Google tell you to tell them to change the chiller? You go tell Google, you guys crazy, man. No? So I said, sure. Yeah, I'll go talk to them. So I go to a base building and said, hey, you got to change your chiller. They want 150 GWP. If you are the base building owner, I own a building, I bought my chiller, somebody come in and told me to change the chiller, what would you say? Get lost? Go ahead, get out, don't want to see you, no? So I thought the base building going to kick me out of the room and said, Luke, you're crazy, man, get out of the room. I thought that's what happened to me, but no, it's Google, right? Well, they want Google. So they said, Luke, sure, we can provide you with a cooling tower and new chiller with a global warming potential of less than 150. Now I shouldn't mention any manufacturer. But there are chillers out there that use 1, 2, 3, 4, C, whatever, that could be well below 150, right? So, yeah, that's the story of that. Have you ever heard of things like that happening around the world? That a tenant can move into the building and tell them to change the chiller? I never heard of that before in my life until this project, right? I'm just telling you what's happening out there. Will that come to Thailand? I don't know. But if you work with Microsoft, Google, Lenny's, JLL, well, guess what? They want to see this thing happen. So the world is changing. That's what I'm trying to say. So we know the world is changing, and we also know one of the important things is we have to be the superhuman beings to try to make that happen. Because in that story I just told you, who's the person that able to talk to Google, talk to this, and try to talk to everybody and try to figure out what's going on? I could do it. You know what's the beauty of that? If you can do that, you got work and maybe more money. Good? I think it's pretty good. My 2 kids are in college, right? I mean, I need the money. So whole life carbon. Now, traditionally, when you think about energy and carbon, you're only thinking about B6. Okay, if you're not familiar with this thing, you better pay attention. This is whole life carbon internationally, everywhere in the future. Traditionally, you think about operational carbon or operational energy, it's only B6. Only that one piece there. If you're net zero operational, by 2031, your operational energy, that's only that piece. So that's 90.1. We're moving there. Now then there's upfront carbon. Upfront carbon is A1 to A3 is product stage. That means those stuff made in the factory, how much embodied carbon that have. And then A4 to A5 is construction. You ship this stuff to the construction site and build them up. Usually those numbers are pretty small, A4 to A5. The industry right now focus more on A1 to A3. All right, upfront carbon. Now you can have a net zero upfront carbon building. That's the second type of net zero. And then A plus B plus C is net zero embodied carbon. So you could have a net zero embodied carbon building if you zero out the A, B, and C. C is end of life, B is in use. So you have the stuff from the factory shipped to the site, got built, and in use stage there's embodied carbon. Wait, what? Why are we, when the building operating, has in use embodied carbon? What if you chip the building's tiles? You have to replace them, right? That's embodied carbon. So that's why in use and end of life, how do you displace it? Yes?
It has to be net zero for each step of the overall net zero.
That's right. That's why there's 4 types of net zero. Net zero operational, net zero embodied, net zero upfront, and finally, if you want a world of zero emission in the future, you're going to have to net zero whole life carbon. The fourth type. That's what we want. Each one has to be net zero in order to get to whole life carbon zero. Is it easy? Yeah, he's laughing. He's like, I'm not doing it. Yeah, so this is going to be too difficult. Yeah, I mean, this is crazy amount of stuff we have to deal with because we never have to deal with embodied carbon until now. What the different certification, if you are lead, is set A3 and A1 to A3 embodied carbon from the factory, you have to do it, right? A4, transportation to the site, you have to do it. A5, how much energy it build a building, optional. And then zero carbon certification on International Living Future, you have to do A1 to A5. And Vancouver Building Code, A1 to A5. But guess what? When it comes to MEP, optional. And then what is B1? What is B1? Anybody know? What is B1? B1 is refrigerant leakage. A lot more concentration on this. Remember that. If you don't remember that, in the next lead version, you're going to hear a lot more about refrigerant leakage. B1. You know, in lead, what's the percentage leakage of refrigerant you use in lead certification calculation? Anybody did that calculation before? 2%. What in reality is that leakage? More than 2, he said. 2% for the leakage for like each year. Yeah. Anybody know what's that leakage? Anybody know, like, did you buy refrigerant for your building? How much did you buy? What percentage of that total volume of refrigerant you have to buy every year? Do you know? Not sure. Not sure. Well, you know, you're not the only one. Everybody in the world is like that. If you ask them, wait, you bought a lot of refrigerant last year, what percentage of the total refrigerant you need you bought? Well, we don't know. Never keep track of it, right? So you're going to start thinking about it because B1 is refrigerant leakage, right there, in use. Now, if you're in Australia, this building we did for Australia, the local engineer said, in our market, you use GWP of below 10. What R410A 2088 will be banned in 2 years in US. Do you guys use R410A here? Yes or no? Yes? It will be banned in 2 years. 134A is 1,300. Yellow, R32, R513A, those are still you can use in US. 4 states has limit for that. And then less than 10 is 1234YF and 1234CE. And R15, R514 is ammonia. Well, that's kind of harmful. But that's what you do in the Australian market. GWP of less than 10, anything in your chiller. You start doing that? No, I don't think so. In US, no. I just specify a project with heat pump on R134A. With the global warming in the future, more refrigerant will be used. So this topic is not going away, and it's going to be a big dollar. But if you want to get to whole life carbon zero, that's all this stuff here. That's whole life carbon zero. One ABCD modules. So what we just cover is whole life carbon framework of the 4 different types of zero you're going to have to think about in order to get to a 2050 net zero world. Okay? What's a typical operational building's energy use intensity in Bangkok for office building? Kilowatt hour per square meter per year. Anybody? Anybody? Less than 200. Anybody else has any number? Something like that? What's a typical energy use per square meter per year in Bangkok? Roughly below 200 is pretty conventional. Many buildings do that. Our buildings do that too. Another question. What is the conventional embodied carbon per square meter in Bangkok? Not there yet. Same here. In US, not there yet. Well, but you know what? We better start used to it. It's coming. So this is the benchmarking. Now this is from European countries. On the left is kilogram CO2 equivalent per square meter. On the right is different typologies. They're different, but ranging to 200 to 1,100 kilograms CO2 equivalent per square meter. And if you count, oh wait, sorry. So roughly about, if you want to look at office building here, it's roughly about 500, say 500, 600, right? Remember that number. Now, you know the cool thing about this? You can forget all this stuff you saw, just remember 500 kilograms CO2 equivalent per square meter. Okay? So in the future, if anybody asks you, well, you guys know what's the embodied carbon of a building? It's, 500. Yeah, let's know that. Yeah. Piece of cake. 500, roughly. Kilogram CO2 equivalent per square meter. Now this is HVAC. So if you add, this is HVAC embodied carbon. A1 to A3, okay? Now you should know A1 to A3. Factory only, okay? Factory only, upfront. So 500 is the number we remember, right? If so, you add up all the red bar, how important is HVAC? The lower one is about 40, so a couple tens and tens. What do you think this add up to? Huh? Almost 100. Anybody else got a different number? So 100 out of 500, or in HVAC embodied carbon is about 100 out of 500 in an office building. Is it a lot? Yeah, it's 20%. Not very significant, right? Wait. What did we say again? This is upfront carbon, A1 to A3, only in the factory, right? How long a building lasts? Oh, what's the life cycle of a building? So most of the time we use 50 to 60 years. In this case, they use 60 years. Does your MEP equipment last for 60 years? Uh-oh. So if you include the replacement, oops. All of a sudden, if you include replacement, B4, okay, B4 is in use embodied carbon. It's not upfront, it's not when you build a building, but it's during use you have to replace them. That's B4. So the replacement cycle, if you add up all these bars now, it's like maybe 80 plus 30, 30 plus 50. What's that?
But doing this gonna extend the building life beyond 60 years, right?
Yes. Well, this is actually 60 years replacement. The gray bar is the 60 years.
60 years
Overall. What's that? Oh, you know what? You actually, so that they can hear your question.
So I said, when you replace the HVAC equipment, right, the building life cycle go more than 60 years.
Oh, no, this is 60 years replacement because the red only good for the first 20 years or 30 years. But then you have 40 more years to go, so you have to replace it at least one or two more times.
If I replace the whole new system, right, it's going to count one again, right?
Yep.
Right. So I have another 60 year, not 40 year left.
You have,
right?
So in this case,
or if I also renovate my buildings, right? Renovate my buildings, it's going to count up one again, another 60 years.
Right. So if your building lasts another 60 years, then you have to redo this again. So I don't know whether I'll go through this here, but tall buildings in general. Okay, why don't I go there? Tall buildings taller than 200 meters from the first day of history to now. How many of them got intentionally taken down by human and redeveloped? Not the World Trade one, World Trade Centers, when a plane fly into it, not those didn't count, okay? How many buildings got intentionally took down and rebuilt? Over 200 meters. So is that so far? Maybe nothing. He's not. Yeah, still there. You know, throughout the entire human history, there's only one building over 200 meters that got intentionally taken down and rebuilt. And that's one of our company's building. All right. But the point is, this stuff, once it's tall, it's not like Denmark. The life cycle could be a lot longer. Because you don't, chances are, when we design Burj Khalifa, we sign a deal, the building's going to last life cycle at least 100 plus years. So it's not going to take down by 60 years, right? Anyway, so what's the total MEP portion now out of 500? Or HVAC out of 500? Huh? How much? 180? Yeah, maybe 200, something like that. So whatever it is, it's a lot more than what it was. And it's actually really significant. That's another reason why HVAC engineers, we have to be superhumans, because nobody understands this replacement cycle deal. If you listen to the conversation out there, oftentimes they say, oh, structure is the most important element. No doubt, up front. But once you include the replacement cycle, especially in tall buildings that potentially last for 100 years, the MEP is very, very significant because they keep replacing it. This is initial carbon only, 20%, yeah. 20% in new building, LCA of a building up to almost 50%. And then initial carbon only fit out is a lot higher, right? And out of the MEP, HVAC is by far the most significant. Much more than electrical and plumbing in terms of embodied carbon. Significantly more. And in terms of system types, what type of system will you use here? VRF? VAV? Chill beam? No. Radiant sealing? No. Heat pumps? No? Okay. So in this chart here on the right are the more efficient door system. So they could be heat pump, they could be VRF, they could be all that stuff, heat pumps that you got, then chill beams, which you guys don't use. But the more efficient system in green, that box, tend to be higher embodied carbon up front. Okay? So in the past, you did a study, it's like, hey, look, you know, our VRF system is really efficient. Well, how about the embodied carbon? And then if you look at the component, that's the insulation duct wrap. It composed of, by the way, this is the first A1 to A3. So you know it's, now you're kind of like an expert, right? Like, and people talk about what's the MEP embodied carbon. You're like, yeah, so like out of 500, maybe 100 is upfront. So if look at that 100, this is about 60, and insulation is that much. And you can look at different insulation type and reduce that embodied carbon. VRF outdoor unit is roughly that much. Rooftop package unit, VAV boxes, sheet metal. Okay, you know what is heavy embodied carbon in HVAC? You probably know it by now, just the way I asked the question, right? By far is galvanized steel. One of them, anytime you have metal, it's going to be big. So this guy here on the right, what is it? Do you know, have you seen this stuff before? Duck socks. Oh, are you supposed to say that? That's not a manufacturer. So that's not, I don't think it's a manufacturer, but this plastic ducts, right? Guess who's the first to provide EPD in like ductwork? Is it a galvanized steel people? No. It's this plastic plastic piping duct people. Why do they provide EPD? Because they look so good, right? Because their product is 17 times less than galvanized steel. So they say, let's go do EPD. Here. Look, we're really performing. 17 times less than galvanized steel. And this is your DOAS, electric reheat, ERV. Anyway, now, this is your equipment. When it comes to equipment, one thing you have to remember is as you go big, bigger equipment has an economy of scale. Per unit embodied carbon or power or energy it generates actually reduces with the economy of scale. So bigger equipment has the benefit of smaller unit embodied carbon. Okay. So what we did was we kind of went through the framework of whole life carbon and we went through the benchmarking. So let's give you a quiz. See who's, should I randomly call people? That would be really bad, right? I shouldn't do that. So what's a general ballpark number of office building embodied carbon? All right. He deserves a big clap of hand. Good job. All right, good job. How about HVAC out of that 500? Up front, what percentage? So what, 100? Okay, give you a hand. That's good. How about the entire life cycle? Roughly how much? 200 to 300. Yeah? Right, so now you guys are experts, man. So you go out there, next time people ask you what's the embodied carbon of a building, I know that, you know, so, yeah, I would say around 100 upfront HVAC, you know. You guys are all experts now. But why do we care? Why do we have to optimize both? You can design buildings. This building here, x-axis is operational, y-axis is embodied, right? So this building is super operational efficient. Agree? I mean, you're not going to get better than that. Oh, by the way, step back a little bit. This is a paper done by a European professor. He actually studied all the possibility of embodied carbon and operational carbon and come up with this kind of data and plot it on a graph. And then this is one extreme of his graph is a super operational efficient building. Look at the embodied carbon, 450. Okay? European building, lower, shorter. That's why the number is lower than 500. But you know that 500, so you know 450, it's lower, a little bit lower. And you know this thing is probably not a high rise. Most likely it's a low rise building. Yes, it's a low rise residential. That's why you guys are all like experts now, right? After like 5 minutes, you can look at this chart, 450 up front. I bet you it's not a tall building. I bet you it's a low rise, and you're right. And then the operational carbon is about 200 plus. That's one extreme. The other extreme is you can do a building with no insulation, right? The envelopes suck everything, just bad. And then you end up a lot of operational energy. You know where's the optimum in this paper you study? Right there. What's the interesting thing? It's closer to a passive building. A passive building with strong envelope to minimize the heat gain and heat loss compared to a really bad building with no insulation. It's closer to a high embodied carbon building. So this is like so abstract. I have no idea what you're talking about, Luke. The point here is you cannot optimize. So you guys are engineers. If you put a circle around operational energy and optimize it, well, you're going to get to like the point here. If you put a circle on embodied carbon or optimize it, then you're going to go to the point like on the other extreme. By the way, people are doing it in US. You look at the news, right? Oh, we have another wood building and it's really low embodied carbon. Great. What about the thermal mass of that building in buffering the energy? Oops, didn't think about that. The point here, you have to optimize whole life carbon to optimize a building. Now let me give you an example of this. This is a Chicago office building, so it has heating and cooling, energy plus, 2,500 square meter, S-rate 90.1. Study 3 types of curtain wall system. 40% window wall ratio, 90% window wall ratio, ventilated double wall. What's a ventilated double wall? Like this. It's a double pane window with single pane on the outside and circulate air through it to ventilate the heat, right? Now that I know you guys are experts on this topic, if I ask you, which partition type has the most embodied carbon? The one this way or the one this way? Like, do it right hand, is that way? Which do you think? Can you raise your hand if you think it's this building here, the curtain wall here, or the curtain wall there? The lowest, the most embodied carbon. Which this way? All agree? This way. Yeah. He agreed. You're a little late though, by the way. But that's okay. So it's the one on the right. So if you optimize the amount of embodied carbon, will you ever do a building like that? Will you ever do like high embodied carbon on the right side? So high embodied carbon, if I want to have the lowest embodied carbon, why would I do that? I would do this on the left, right? 40% window wall ratio. Now, actually, by the way, why we do that is Chicago still is a place that they like full height glass, the American developers, right? So you are forced to do oftentimes 90% window wall ratio even today. Because they buy the best, same to China developer, right? They buy one of the most expensive lot, and you go there and say, you know what, I'm gonna put a lot of opaque wall so you cannot see the view. Well, how do you like that as a developer? They're gonna say, Luke, get out of here. We don't want to see you anymore. Oh, thank you very much. Doesn't work. So they want full height glass, and that's why sometimes you have to use this ventilated double wall or some way to attenuate the envelope. Much higher embodied carbon on the ventilated double wall. Now the dotted line is extruded polystyrene insulation. The solid line is rock wool, which is a more natural material. That's why the embodied carbon is lower. Now here is getting interesting. Compared to a full height glass, the middle scenario, the right scenario with the double skin facade, the embodied carbon is orange. What's the white color? The white color is VRF system. What's the refrigerant you use in VRF today? 410A. Now that these expert panels, do you remember what's the GWP of R410A? What's that? What's that? A lot. Oh, I like it. It's like, you got to be like a lawyer or something, you know, it's like avoiding the number, but I know it's a lot. That's pretty good. So yeah, it's like what? 2088. That's why if you can reduce the amount of VRF capacity you have, you reduce the refrigerant and subsequent all the leakages. So the embodied carbon is a lot lower. In this case, the added embodied carbon of the curtain wall plus the VRF reduction, the ventilated double wall is the same as the middle scenario. And if the developer wants full height glass, and if you think about that, this two has the same performance in terms of embodied carbon. Now here's the $1,000 question. Oh, what's the dollar in Bangkok? It's not dollar, right? What do you call that? Huh? Bar? Actually, he will give you 1,000. Think about it. I don't want to give you anything. Maybe he will give you. Which one will operate better, the middle one or the one on the right in terms of operate energy? On the right. So most people got that, and that's what you see. Now it's Chicago. The red is heating. So a lot less heating, right? That's the energy performance. So what's the story here? The story here is you cannot look at things in silo. You have to look at this thing integrated, the exterior wall, the HVAC system, the operation and whole life carbon, optimized it together. Then you'll figure out actually the option on the right, if you are into a full height glass, is actually pretty good. It's actually eco and body carbon to the middle one, but whole life carbon is much lower. So that's why you have to optimize whole life carbon. Oh wait, how long did we talk? Oh shit! I'm sorry, not supposed to say that. What time are we to end? 2:30. Okay, 10 minutes. Okay. So I'm so sorry about that. I'm not supposed to say that. Just slip out of the tongue. Whole life carbon example. Huh?
It's a kind of fruit.
Oh, that's exactly what I meant. I just like to eat that fruit. Thank you very much. I was like thinking about that fruit all night long. So this is, let me give you an example. This is my first project, and this is not that long ago. This is like 2 years ago. I was like you. I never did one of this project, and it's like they say, look, start looking at this. I'm like, yeah, sure, I'll do that. So we got help from Argonne National Lab to do this. It's a 1,600 square meter building. By the way, this is Chinatown Library in Chicago. It's an award-winning architecture building of its simplicity. And it's easily get to from downtown Chicago with the train. There's an oculus in the middle of the building. That white skylight is oculus to the sky. And then the black thing, radiant system. If you can deal with the loads, radiant system is one of the most efficient system in the world because everything is water cooled, right? So it's super, super efficient in terms of energy. And that's the section of the building, 2 stories with an oculus, shading on the outside. You see the radiant system on the 2nd level. The stairwell in the middle. Those are the assumptions, 60 years life cycle. We're not going to go through. Energy performance is pretty good. We actually has plenty of shading devices to reduce the solar gain. 29.2% reduction in solar radiation. Okay. Huh? What is it good for? Reduction of solar radiation and also reduce some glare. No, yeah, just on the outside. So maybe you can see if I can. There's a little bit of that here. You can see. It's a little bit less glare and Now, but this is the part that typically we don't do. We actually go detail account for every single element in the building, from substructure, superstructure, envelope to kind of develop the material quantity of each type of material in terms of meter square. Meter cube. Meter cube of material, and then times the GWP of the material to get the carbon. So just like the refrigerant, you have the refrigerant and then the GWP, you have the material, you times the GWP, you find out the carbon emission. So that's what we did here. In terms of operational energy, the green line is like the baseline electricity. The orange is the electric consumption, right? More in the summer, uniform year-round, and the blue is heating energy. Mostly in the winter, and then a little bit, there's nothing in the summer, a little bit in the fall. And it's done by natural gas of this building. So that's the energy profile of the building. Now, if you, by the way, now that you're whole life carbon expert, What's the life cycle again for a low-rise building typically? How many years? I forgot already. What's the life cycle of a low-rise building? How many years? 50, 60? Typically 60 years. Internationally, 60 years. Okay, remember that, 60 years. So if you use 60 years, and then that's the operational energy of what we look at, and orange is embodied carbon, that's what you have. And gray is the refrigerant. Okay, gray, refrigerant, orange, embodied carbon, blue, operational carbon. Now on the right, if your grid is completely clean, if you are all renewable, then you got rid of all the blue or the operational carbon. It's only like embodied carbon and refrigerant. What's wrong with this picture? You know, one of those trick questions like people throw at you, they give you a picture that looks right and say, okay, what's wrong with it? What's wrong with this picture? The what? Yeah. She's saying maybe the operational energy cannot be zero. Even the grid clean, maybe there's some carbon. Actually, she's right up the right track. So, year one, this is year one, right? Majority of embodied carbon, a lot of refrigerant. The blue is operational. This is year one. Okay? Oh, what happened? Wait, now, hold on 1 second. What did we say? This is a 60-year cycle building. So 60 plus 2023, what year is that? 60 plus 60 plus 23? 83. When did we say U.S. gonna net zero by? 2050, not 2083. So like what she's talking about, there's a renewable. This is business as usual for 60 years. But it is not business as usual. The world has committed to a different future. Right? Remember the very early projection that we said the world has changed? No longer 6 degrees Celsius. Because it's renewable energy future. If that's the case, let's assume we have a renewable energy grid by 2035. Her comment is the future grid may have a different impact than today. So if that's the case, this is what happened if the grid is all renewable by 2030. That's blue. That's orange is embodied carbon. Why is 2030? Why is 2035? Because the U.S. government, Biden administration, just came out this year and said they want the electricity grid by 2035, 100% clean energy. So if that's the case, and this building is all electric, converting natural gas to all electric, that means by that year, there's no more emission on operation. It's not this continue last forever linear projection into 60 years. It's only like from now 2023 to 2035, 12 years. So the blue is a lot smaller. If that's the case, what's your focus now? Is still operational or embodied? Embodied, because it starts dominating the discussion. Initially, if you still remember, the discussion is, of course, like we all do in our career, is operational carbon. Look at how serious it is. But if Thailand truly committed by 2050, the country got cleaned up. If there's true, now that's a big if there, your focus maybe start drifting into embodied carbon because the operational carbon will stop at 2050. Now later on we're going to see an example of how that is not even true. We're going to go one step deeper. So how do you get there to a decarbonization future? First, optimize the building envelope. We saw example today, right? Because you do that, you reduce the HVAC system, refrigerant and all that stuff. And then you have material and energy efficiency in terms of operational and embodied. Utilize waste energy. Embodied carbon, start accounting for it. electrified loads, converting natural gas to electricity, because natural gas, now here's the future. If you keep on using natural gas, it will be like that till eternity. But if you use electricity, and if 2050 is got cleaned up, then the graph is gonna go down like that. So it's gonna be converting to electrified low GWP refrigerant, 410A. Boy, it's gonna be a little rough. Demand side management to minimize the demand of the building and carbon-free energy. So that's kind of the roadmap to get to net zero whole life carbon. So this is the first whole life carbon. And we're going to take a break here. And what we did today is first we frame out for you what is whole life carbon, ABCD module, and we talk about why you cannot just optimize operational. That's not going to be optimized. You have to optimize whole life, embody and operational together, right? And then we look at an example of how do you do whole life carbon in a Chicago building. And finally, we look at different ways or the way to go to net zero whole life carbon future through these measures. We're going to take a pause here, and then we'll come back and look at the final version of this.
So what you said is that after we have a clean energy product, right,
Yeah.
the embodied carbon will be responsible by the manufacturer only, right? Not on the user like us. On
It-
the manufacturer
you will-
only.
So you will see, so embodied carbon is partially from the manufacturer, and you will see later we will be responsible too. In our spec right now, we actually specify products that has low embodied carbon, and then request manufacturer to provide. So the priority is given to the manufacturer that can provide embodied carbon information in our spec. And so that is our work. We're going to have to work together. It's going to take the whole village, the whole thing, to get to zero. So we're going to have to specify things. They're going to have to know the information to get to zero.
Operator, right, we are enforced by the government that we have to use the clean energy to operate the building. We already enforced.
Maybe you can speak to they can hear you too.
Because as an operator, right, we are enforced by the government agency already, right? By, let's say in the US, you said 2050, right? We have to use clean energies,
Yeah.
right? So the embodied carbon gonna be responsible only by the manufacturer, because we left just only the carbon that produced by the manufacturer, not by operator like us.
Yeah. Yeah, so yeah, the manufacturer will provide you the information. You will be the one specify which product you want to use. So you have the role of trying to accelerate the market that have low embodied carbon. So when we come back, we'll have the home stretch. So I'm going to tell you, give you a little heads up here, it's going to be like one level deeper than. Now, since you are already prepped to be the carbon expert in this section, I think you're going to do very well, because the next section is going to be take you to a different level of whole life carbon expertise. So, all right, are you ready? So go take a break and get some caffeine. Next one is going to be intense.
And will be hand over to Mr. Luke once again. Thank you.
You know, I want to apologize to you, because I look at the slides here, I realize this section, the slides are not provided according to this thing, and actually the earlier sections, the slides were not according to this too. It was my bad. I changed it, nothing to do with the organizer. They did a really good job to asking me for the slide, but I changed it after I submitted, because I figure we're going to have some really high quality people, so I ratchet this last section to be a little deeper and higher, and you will see. So the slides are not according to this. I start looking at Bangkok and realize, well, this is no Europe. The buildings are taller. So I'm gonna detour a little bit to touch about tall buildings. This is Seattle. When you look at this picture, you will see kind of this mountain thing in the middle, tall buildings, and then it kind of drop down to kind of this carpet thing covering a lot of the ground, the low-rise building. The mountain composed of 5,000 buildings out of 181,000 buildings in Seattle, city of Chicago, Seattle. So it's only 2.8% of the building by count the tall buildings. 2.8% of the numbers are tall buildings. But it accounts for 45% of the emission in Seattle. It's actually not different than usually cities. Anyway, 45% of the emission is from those tall buildings. Manhattan, New York. Buildings over 50,000 square feet are less than 2%. Okay? But account for 48% of the emission. So the big tall buildings, they emit a lot of stuff. Like we actually, by the way, our company designed Bangkok 1. So it'll be interesting to see how much energy that building uses. Same thing for Minneapolis in US, 1.1% of the tall buildings, you can see in the picture, account for 47% of the emission. So the big and tall buildings tend to be very energy massive and carbon massive. So tall buildings is not the same as low rise, all right? Why are they not the same? Temperature. When we did Burj Khalifa, the left is balloon data, the middle is our modeling of the temperature. On the right is actually taking infrared picture. You can see the temperature drop as it goes up. Okay? So as you go up, temperature is different. Now for those who are involved in tall buildings, the weather file is different. When you calculate energy modeling, the weather at the base of the building, in this case is Dubai, at the ground level is red, right? And you can see different temperature and how many hours it falls into that different temperature in the entire year, the ground level. And on the top is 600 meter in Dubai. We generate this weather file so we can run the energy model, and it's different. So if you have tall buildings, they are not the same at the low rise because at the top, it tends to be cooler, right? And the entire weather file you're going to run the energy modeling is different. So that's number one. Number two is much longer life cycle. We touch on that. I decided to give you some slides so you have some reference here. Since 1920 to 2019, right, there are 1,628 buildings taller than 200 meter. Almost 1,700, 1,700 buildings. Many of them built after 1970s, but I mentioned to you there was only one building got taken down intentionally. This was the building. It was SOM building in New York City, Park Avenue. So their life cycle could be very different, right? Not 60 years, could be much longer. We don't know how long. As a matter of fact, we don't even know how long, because none of this building are taken down yet, so I don't know, right? Until they got taken down, then you know, oh, okay, you know, there's like 25 of this building got taken down now, and it has been whatever, 100 years, 200 years, who knows, right? Nobody knows right now. Now, tall building also, like x-axis is the number of floors, increasing in floors. Y-axis is the embodied carbon. The R square is a little low, but in general, the curve is going upwards, meaning that higher the floors, the intensity of embodied carbon is higher, meaning that the amount of embodied carbon per unit area is more. Per meter square is more embodied carbon. It takes more. And here's why, because when you build a structure, you have to put more stuff at the bottom to support the height. So there are more stuff per unit area. And also energy consumption tend to increase per unit area. Why? Because you need higher elevator, faster elevator. You need to pump the water to the top, push the electricity to the top. All those consume more energy. So in general, tall building consume more. This is a regression on analysis study of 2,000 buildings in US, and you can see x-axis is the area, y-axis is energy used per unit area. Don't worry about a unit, it's in inch pound rather than metric. But the idea is the energy use intensity increases with amount of building area increase. So how do you get to zero? Okay? Operational energy, now that you're an expert, right? That's B6, operational energy. How do you get to zero? Can you get to net zero energy on site with tall buildings? Like inside the building site itself? Can you get to net zero easily? No. No. Not easy at all. Anything taller than like 4 or 5 story, super difficult already. So this building is Pertamina Energy Tower in Jakarta. We got to net zero on site. How? Very difficult. So you know what? Jakarta Pertamina Energy is a geothermal power plant company. So during design, we let them know that, hey guys, you are providing geothermal power. Now this is deep geothermal power. This is about 2 kilometers, 2,700 meters down, grab the very hot water to generate power. So we said, you provide this to many of the Indonesian districts. When you do your headquarters, do you want to walk your own talk? They said, yes. So they build an on-site geothermal power plant that goes down to 2,500 meters to 3,000 meters and grab the super hot liquid to generate electricity and get to net zero on site. If you have to count on that sort of thing to get to net zero on site, how many buildings in the world can get to net zero? Not that many. So it's not easy to get to net zero operational energy on site. You're going to have to count on site and off-site renewable energy, oftentimes off-site renewable. So it's easier if your country or city has a lot of off-site solar field, right? It's not so easy if you don't have area to put the solar field. How about embodied carbon? How do you get to net zero? If you think operational energy getting to net zero is difficult, how do you get to net zero embodied carbon? How do you do that? Well, one way to do that is the grid is completely clean, so everything is renewable energy, so all the production is carbon free. That's easier. But we saw this before, 500 to 600. We're not going to go through this section here. Oh. So, by the way, I really like that because you guys are so expert now. What you're looking at is the net zero embodied carbon roadmap for the City of London. Okay? Now let's use our expert eyes to watch them to see if we can detect anything from the City of London making sense or not. First of all, they said today's world, the business as usual, all the way to the left, is 800 to 1,000 kilograms CO2 equivalent per square meter. A little bit high, right? We know it's 500 for office buildings, so it's a little bit high. But they said their 2020 target is 500 to 600, that's the pink and the red bubbles, 500 to 600 kilograms CO2 equivalent per square meter for embodied carbon. Fair or not fair? Fair or not fair? Yes or no? fair, right? So yeah, it's possible. But what's the green bubble? City of the London consultant suggesting 30% of the material are from recycled material so that it doesn't use much energy. And 50% of the end of life of the building go back to recycle so it doesn't go to waste. That's their roadmap trying to get to zero. So that's today. What about 2030? Now the embodied carbon number is lower, right? It's no longer 500 to 600, it's 300 to 350. Why? Because part of that is they're recycling 50% of the new building from recycled material. 50%. And when the building is done, 80% of the cycle 80% of the material go back to recycle. Is that easy? Any of your buildings are done like that. Significant amount of material go back to recycle. Is your chiller done like that? What do you do with the galvanized steel ductwork? That may be easier. Actually, you could go back to kind of reuse them. But how about your that? Concrete, that could be break down some of them, recycle. Steel is easy, right? HVAC is kind of tougher. Diffuser, how do you maybe melt the metal and reuse them, right? So what about 2040? They aim at 2040, zero. 2040, they are seeing -100. I don't know whether you can see that number there, sorry. In the top there, they're aiming at -100 embodied carbon in negative. And how do they do it? 100% recycled material go to the building and 100% of the material come out of the building is recycled. City of London consultants, that's their roadmap. Is that easy? No. Who's the crazy person to come up with that idea? But the idea is if you can recirculate, recycle everything, you will get to net zero. That is called a circular economy. Have you ever heard of that term? Circular economy. If you haven't heard it yet, you're going to hear it a lot more from the manufacturers, from the designers, from everybody. A future world that everything recycled. Well, we know that world at one time when we go back to the health of the humans. At one time, everything recycled, right? We eat the plants and then we give our good stuff back to the plant and just recycle. So, by the way, recycle element, S-Ray is working on one of the first standard. If any of you manufacturers, designer, whoever you are, government people, if you are interested in circular economy, we are working on a standard called TM66 with the UK version of S-Ray. The idea in that standard is actually specifying a lighting fixture, 100% of the material from recycle and we go back to recycle. So that is start making us to think about a world that works differently. Everything is recycled. Because otherwise it's really difficult to address the embodied carbon question. And it's even more difficult when you have to address in the future, you're going to need 2 times the amount of building than we need today. We are positioning for different future. Now this portion here is kind of the final portion of this, is give you an example of whole life carbon to think about different things. 4 dimensions we're going to think about: high performance building, net zero operation emission, refrigerant, carbon dioxide discount rate. Let's go to the first dimension first, high performance building. Now the way we'll play this example is we do a building of 10,000 square meter all electric building, upfront carbon 400 kilogram CO2 equivalent per square meter. So by now you know this number is slightly better than average in an office building, not by much, it's pretty reasonable. Operational carbon is 125 kilowatt hour per square meter per year. And the grid emission, that means every unit of kilowatt hour will generate 370 gram per CO2 equivalent per kilowatt hour. What's the grid emission in Thailand? Anybody know?
600 gram of in 1 kilowatt.
Wow. You really need to give the mic to her. She's the only one in the... Anybody knows the number differently? Oh, you gotta give the mic to her. Let her speak again. 499? 5499? Go ahead. What's the number? So she speak and what's your number? About 600. 5499. 54. 054. Okay. So it's about 550 grams, 600 grams per kilowatt hour. How's that compared to the world average? What's the world average? No, good try. But that's not the number. That was just an example. The world actually really easy to remember because the world average at about 500 gram of CO2 equivalent per kilowatt hour. So you're slightly above the world averages. So you got more work to do compared to the rest of the world because you're above the average. You're 549, right? About 600. So this is 370, so it's cleaner than Thailand's electricity grid, okay? Now your upfront carbon is 400 times 10,000 meters square, so that gives you 4,000 tons of carbon upfront. Okay, that's your upfront and body carbon. And then because of the replacement cycle, remember that in the MEP you have this replacement cycle, that's your total life and body carbon. And if you are 125 kilowatt hour per square meter per year, you're going up like that in 20 years. Okay? Oh, by the way, this is the first 20 years. So you replace only one time in the MEP equipment. Now, what if you have a building that is much more efficient than this one? What's the impact? Okay, let's have a building much more efficient. This is only 62 kilowatt hour per square meter per year building. Much more efficient, half more efficient. You know what we want to do? We want to look at how's the impact the whole life carbon. Okay? So given this assumption, boom. Operational carbon is orange, blue, and body carbon. So a more efficient building, the embodied carbon is more important. Make sense? Right? If your building is more efficient, of course the operational carbon is not as important. Embodied carbon is going to be more important. In this case, it's 70% operational for the more efficient building, 82% operational carbon for the less efficient building. But this is 60 years. Now, by now, I bet you all know that 60 years is not very realistic. So we'll see what happens. Net zero operational emission. What if we draw a line at 2040? Now, in the last section, we know for sure if you draw a line there, the operational emission is not going to be as important. And here's why. Because in order to get to zero of if the electric grid has to be all cleaned up by 2040, you will end up doing this. Linearly, the electricity per kilowatt hour has to start dropping every year. It's not going to be like we're going to be, if you have bank quote, right? It's not going to be, we are 550 until 2050, boom, we're going to go to zero. It won't happen like that. It's going to be, we are 550 here per kilowatt hour, gram CO2 per kilowatt hour, and we drop to 500, linearly to zero. That's what linearly go to zero. When that happens, what happened to the operational carbon curve is obviously don't do that. right, linearly. It's not going to project linearly. What happens is you just bend the carbon curve. What's bend the carbon curve mean? It means like this. Because your operational per year is, your electric grid is keep cleaning up. So you just bend the carbon curve. This is huge in terms of concept. Is Thailand going to bend the carbon curve? If you're going to bend the carbon curve till 2050, you will be seeing a very different future. Your carbon emission on operation is like that. And if you go back to the chart, all of a sudden, your operational emission on the 125 is 47% only, and the more efficient building, it's only 30% is operational. Because you just bend the carbon curve. Because you put a day in there and saying our grid is going to get cleaned up now. We use 2040, but you might be 2050. So we put two cases side by side for you. On your left is business as usual, and the operational carbon is orange. On the right is 2040 net zero operational, and the 2040 net zero operational, and the orange again is the operational. So you can see very different future. Who's controlling the future? Who's controlling which one's going to happen? Yeah, I think so. I think it's the government. I think it's discussion like this. Everybody potentially is controlling it. And this is happening in Thailand, definitely happening in US. I went to Japan. Japan has the same discussion, and same as UK, and same as every single country, same as China. I bet you there were some people like in China, like doing things right now. It's exactly like this. Are we at 500 on the embodied carbon of a building yet, or where are we? Are we going to be able to bend the carbon curve? And the answer is nobody knows. But it's going to take the whole village. It does take the whole village, everybody. But in this process, whoever know more and able to figure out this stuff earlier, they potential could be leader to change the industry, right? So refrigerant, the impact of refrigerant is like this. Initially, refrigerant come with the building, and then it leak as B1. Now, it's very different than B6, which is the operational. In fact, they are not the same, B1 and B6. Why is that important? Because now, did anybody involved in scope 1, 2, 3 emission of a Fortune 500 company? Not yet, but you will. The next step is you're going to have to, you will hear a lot more, because many Fortune 500 companies committed to kind of a net zero future. The CEO say, we are a 1.5 degree C company. The CEO committed it. Do you think many of the CEO knows exactly all this stuff here? They have no idea what they committed to. They say, oh, we committed to this net zero future. And we're going to do scope 1, 2, 3 emission. Have you ever heard of scope 1, 2, 3 emission? Yes? No? Yes? If you're going to have to deal with scope 1, 2, 3 emission, scope 1 emission is under fugitive refrigerant, is under scope 1 emission. Okay? Refrigerant leakage is under scope 1 direct emission. And but it's B1 in the life cycle, so you got to be careful about that. Refrigerant leakage is scope 1 direct emission, in scope 1, 2, 3 emission. So if that's the case, it increased the upfront carbon 10% more, 20% more in the life cycle. And if 2040 is the cleanup day, the question is, will refrigerant continue to be the same? Okay, in the next replacement cycle, right? You buy a new chiller, Is it going to come with the same refrigerant? What do you think? Huh? Probably not. So your embodied carbon could change, but we don't know. So you have to make some assumptions there. But refrigerant is roughly about 4 to 6% in this example. But if it is 2040 net zero operational, it becomes a lot more important because the operation, the orange just got dwarfed by 2040 net zero. So here it is. Again, business as usual is on the right side. And you see the refrigerant. The gray is the refrigerant. The left side is 2040 net zero operational. Refrigerant becomes more important. That's the case. Finally, I don't know whether you guys remember, early on in the section, we said Denmark looked at 50 years of the embodied carbon and 50 years of the operational carbon and divide by 50 and come up with a number. What potentially is tricky about that, assuming, let me give you an example. Anybody will do this deal, I will do it for you right now. I'll give you, no, I won't do that. You will give me $100 today. You will give me. And I will give you $100 10 years from now. Who will do that deal with me? Why wouldn't you do it? Because, what's that? Time value of money, right? What's the discount rate you typically use? The inflation of the dollar, right? If the dollar inflates by 3% per year, so divided by 68, it will be double in 24. So you're losing out pretty good. So nobody will do that. What about carbon? What's the discount rate of carbon? Time value of carbon? What is it? When somebody said, I emit a carbon 10 years from now, is it the same as I emitting carbon today? This is actually, there's no fixed rule out there yet, so it could be, you can go either way. Who said, I emit a carbon today is the same as 10 years from now? Who think that is probably the same? Who doesn't think it's the same? A carbon emit today is different than a carbon emit 10 years from now. There's a bunch of you thinking different. Why do you think different? You want to try it, or you want to try it? Anybody? You want to use the mic so that they can hear you? Oh, why don't you go first? Oh, no, here. There you go.
The impact of the carbon dioxide emission in the future is very, very costly.
Yeah.
So
what you're saying is, if I emit a carbon today, I impact the atmosphere for 10 years before that guy emit another one. It cannot be the same, right?
10 years later, people around the world will face the very, very unconventional emission impact.
Yeah. So it cannot be the same because of that.
Yeah.
Time value cannot be the same. What do you think?
It depends on how dangerous it is when we face in the future for our environment.
Yeah.
Right? If the environment getting worse, the carbon is more expensive.
Yeah.
Right? We need a lot of carbon reductions, more than at present.
Yeah. So it may not be the same value because of that, right? Now, in the country of Denmark, by dividing everything evenly to 50 years, what did they assume? The time value of carbon is the same for those 50 years. Very easy for everybody to understand, divided by 50 years, simple, but it may not be correct because the time value of carbon is very different. So what's the time value of carbon US is using? If you work for a US government project, the discount rate of carbon social cost. Now cost is easier. Once you put everything into cost, there's a financial term, you discount it to the inflation rate and the value of money, right? So that's easier. So for the US government, the discount rate of carbon in the social cost is about 3 to 7%. So depending on which administration you are in, right, if you discount carbon at 7%, the impact of carbon is very small in the future because it doubles 10 years divided by 68. So it's very small. But so depending on what message the government want to send you, they can discount carbon at 7% or discount carbon at 3%. Big difference. And the time value of carbon using the National Renewable Energy Lab in US, the built-in discount rate is roughly about 3%. Okay? What's the discount rate of carbon in this country? Nobody knows. I don't know. Do you know? I guess you don't know. Even in many countries in US, the discount rate of carbon, I just give you a couple examples of what the government and NREL is suggesting, but it's not established. But we know chances are like what they said, and I agree, the value is not the same. If you apply that discount rate to the discussion we have earlier, you're going to have curve like this, further bending the carbon curve. All right? So you will have in the 2040 net zero future option, this is with or without discount rate. Okay? Because 2040 is very short time, you discount everything by 3% is not a whole lot, right? There's only like 10 some years to discount. But if you discount everything to 60 years, business as usual, then you could have some significant number just because of the discount rate. So that's the business discount. So that's a carbon discount rate if you apply to it. So you know, we cover a lot of ground today. I don't remember last time I talked anything for 4 hours. That may be the first in a long time. But we start with one big topic. The topic in the morning was really about the population growth. Much of the discussion we have today is the population growth into 10 billion people and the subsequent consequences of people getting older and more old people and the potential health impact in pandemic and after. That's kind of the morning thing. If you're an architect, if you're an engineer, in the past, we designed a space to keep human beings in. It's no different than putting a monkey in a conference room. But in the next few decades, it's going to be important to design not just a building, but a habitat. Habitat for human. Habitat is where that species belongs. It works with the species rather than a space to put the species in. Kind of like a monkeys in a conference room. So we need to think about that because at the end of the day, how many people actually heard about the whole topic of microbial and all that stuff before this today? Anybody? If eventually we're designing buildings for people, should we know better about who we are before we're designing the space? So that's something to think about, who we are. How we're different. Microbials, we don't know enough about it, but we should know more. Our own rhythm of the circadian rhythm. In Japan, the thermostat, one of the building I visit this time, some ideas for you, right? One of the building I visit, the thermostat is mobile. So it's not on the wall. You could put it on the table, you could put it over there. The idea is not a static environment, right? It's a dynamic environment. The room may have one person and the person sitting over there. So why do you need the whole room to be comfortable? So they have a movable dynamic thermostat you carry with you. And then they have demand space toilet. There's a sensor in the toilet that can actually exhaust per the amount of pollutants they measure in the air. How about that, right? So there's stuff like that happening to kind of design this more along the line of a habitat for human. And then subsequently in the afternoon, we start looking at the whole idea of whole life carbon framework, the benchmarking. And then in this section here, we look at how taller buildings are different, how to get to zero in operational, not easy, maybe off-site renewable. And then finally look at embodied carbon, how do we get to zero? And certain concepts like bending the carbon curve. Because, let's face it, outside of this room, how many people in Thailand knows about bending the carbon curve? I bet you it's not that many. But it's the people who's going to know that because this is happening with some of the Fortune 500 companies who are concerned about their scope 1, 2, 3 carbon emission reporting. They care about their scope 3 emission, but they don't even know what to measure, because if you go to those Fortune 500 company and ask them, hey, what's the refrigerant leakage you have last year? They will tell you, I have no idea. But they account for their scope 3, well, that's their scope 1 emission, right? So we gotta start changing the industry and lead the industry to a different place. And that's going to be hopefully the job of the architects and engineers who are educated in this front. And this is more of a science than art. It's not going to be a person that know just the art side of a building able to attack this issue, because it's a lot of that is very engineering and science oriented. So it's going to be more the scientific community, the engineering thinking community is going to address that. And it's going to be happening. So in reaction, you have a choice. Obviously, you can do nothing and wait for it to happen, right? Or you can start making the change yourself. Make that happen, and in that process, lead the change and try to create a better environment. But there will be so many unknowns, right? So we can try to work together. For example, TM65 for Thailand, for example, right? Using this to calculate the embodied carbon of the equipment, develop that standard. We actually have a team in US developing the US standard, so we can help to develop the system for Thailand, for example, to make all those happen. Because sometime in the future, if we truly believe this 1.5 degrees C is important, 2050 is something Thailand committed. Thailand committed to a 2050 and 2060 target. Who's going to make it happen? Right now, outside this room, that's not that many people even know about bending the carbon curve. So you have a choice. It's up to this group here to how to create that whole village to go out and try to make a change. And in that process, by the way, it's usually good business. You can make money out of it. Because we're going to see 2 times the built environment area growth in the future. So have some fun, make some money, be a superhuman, and save the world. Thanks. So is it a discussion thing you want?
I
I do have the question about the carbon discount rate,
Yes.
right, that you just mentioned. Because, I mean, the number you said, 3 to 7%, right? Okay, if we think on our side, if I put it on the lower number, right, that means I leave all the responsibility on carbon reductions to the next generations, not to my generations. Right? So the number is not just depend on us, but it depend on, our next generation as well, right? And it's also depend on the cost.
Yeah.
Right? If I put higher number, it's on my own cost, a lot on that, instead of on the next generation cost.
Right.
So the number is very hard to figure out because it's not on our own decision. We have to think about the next generation as well. We want to do it. If we want to take the responsibility on our own, right, the number should be higher, not low. That's why they
Yeah.
call it the social cost.
So if you have a high number or percentage, that means the future carbon, when it discounted today, is not as important because you have a very high discount rate. It's not as important. So your focus will be maybe more on today's carbon. But one thing for sure, you're right, is nobody knows. When it comes to a lot of these rules, I mean, think about the opportunity here. There's so little rules out there. You can define a lot of these rules. Really. In Thailand, in Asia, you can define, I mean, you can lead that process with the others, work together to define it. So that's an opportunity for us today to take the leadership, right? And you're right, that piece of about carbon discount, it was not figured out yet, and nobody knows. But like what he said, depending on how we want to shift the burden from now till the next generation, we can use different discount rate, but we also in that process make up the rules. But hopefully we are not, and I don't think we are, right? We are not, well, I have 3 kids, you know, so I don't want their generation to suffer either. In fact, every parents want their kids to do better than them, right? So it's that sort of discussion of trying to create a better world for the future generation. Really, we want them to do better than us, for sure. But yeah, there's no rules, so we have to figure it out in the right way.
Okay. Everyone, do you have any question for the last? Okay. Good afternoon again. Let me introduce yourself because in the morning time I'm not available. Yes, I am Mr. Suvachai Chungchit Damlong, CTTC of Ashley Thailand chapter. Actually, I am the person that will responsible by today for this seminar. But I'm not available, and Mr. Pichapat to take action instead of me. I have to say thank you very much to him. Mr. Pichapat is our president, yes, and I have to say sorry for everyone and Mr. Luke as well. Okay, next, we would like to invite Mr. Chaichan, representative of Air Conditioning Engineering Association of Thailand, or ACAT, to say some close speech for this seminar. Closing speech, yes. Oh, yes, because today is his birthday. Yes. Okay,
Birthday
please.
boy, birthday speech.
He doesn't tell me before to do this.
Yes.
Surprise birthday gift.
Surprise!
Anytime.
ก็ in Thai first
ก็ผมว่าวันนี้เราได้ความรู้อะไรเยอะนะท่านอาจจะมีความรู้เยอะอยู่แล้วแต่ของผมเนี่ยมันเป็นแก้วที่ว่างเปล่าไม่มีน้ำเลย มันเติมเข้ามาเยอะมากเลยไม่ต้องแล้วก็คิดว่าต้องเข้าไปหาความรู้เรื่องนี้เพิ่มเติมละเพราะว่าเขาพูดมาตั้งหลายคำใช่ไหมฮะ bending carbon curve อย่างนี้โอ้โหอะไรมีกันบ้านต้องไปศึกษาเยอะแต่ว่าปีที่ประเทศไทยจะทำ net zero คือปี 2050 ใช่ไหมฮะตอนนั้นผมคงจะไม่ค่อยรู้เรื่องแล้วเพราะตอนนั้นก็คือ 97 อายุ 97 แต่ไม่แน่นะจะพยายามอยู่ดูความก้าวหน้าประเทศไทยหน่อยลองอินไทย understand some picture
Luke is a good man, yes.
okay. I just told them that it's today for me I think myself is like a empty glass and you pour a lot of knowledge to me and I got a lot of new words like bending carbon curve. So I have a lot to do, to read, to listen, to see, and wait for 2050. 30
And
years.
live for another 70 years.
That time, because Thailand have a campaign that will be net zero carbon in 2050, which I will be 97 by that time.
Don't worry, you will live till 140. So 97 is only halfway there. So.
Okay, let's give a big hand to him. And thank you. I hope you will come back again soon in Thailand.
I love Thai food. Just let me know anytime. I'll come.
Okay.ครับ
Please go to in front and take the photo and
จะมีวินเช็คกับโฟโต้อ๋อเดี๋ยวประมาณไหนซูเวเนียใครว่าลูกชิด
We gotta get that tonight. Thank you. Thank you so much.
everybody in and yes ครับ